So yeah, let's get started here. This is Module 7, the last module before the final exam. So this is essentially the end of the new material we'll be going through. Yeah, like I said, 39 questions. So we'll probably split this to two parts. And we're looking at some exponents here. So this is just an approximation. So there's really nothing difficult about this one. You can use any calculator here as long as it has an exponent function. So I'm just going to use this one that's in my that's on Windows. So the exponent button on this calculator is x to the y. Sometimes it's given with a caret. So on this one, let's say I would do 6 and then xy, and then notice in the top line it says 6 and a caret. So another way to do this, if you don't have a nice calculator app, you could use a physical calculator, or you can just type this into Google exactly as it appears on top, and Google will give you the answer. Okay, so 6 to the 2.2, and we get, a long number. This is most likely an irrational number, so that means that the decimals will go on forever and ever, and the computer's memory just limits how many it's able to display. So 3 places, that means 51.514, and then we have to look to the 4th place to round it. So if it's a 5 through 9, we're going to round up, and if it's a 0 through 4, you keep the number as is. So because this is an 8 after the 4, that means we're going to enter 51.515 in this example. And then this one as well. This involves a special number, so Euler's number is very important for exponential functions. So for number 2, let's just write down what that is. So number 2 is Euler's number. So it looks like Euler, but you're really supposed to pronounce it Euler. Named after the famous Swiss mathematician. So this number E is maybe the second most famous irrational number in math after pi. So its decimal expansion is going to continue forever and ever without any pattern or recognizable string of digits, and it just goes on forever and ever without repeating or terminating. And it actually comes from, where does this come from? The actual definition, it involves a limit. It's actually, so the limit as n goes to infinity of 1 plus 1 over n to the nth power. So that's kind of a weird thing to think about, because inside the parentheses, the quantity is getting smaller and smaller and smaller, and then it's being raised to a larger and larger value, right? So you can start just by counting, by looking at what this pattern would approach as n got bigger and bigger and bigger. So if n were 1, what would we get? 1 plus 1 raised to the first power. So we would get 2. And if you had, say, n equals 2, we would have 1 plus 1/2 raised to the second power. That's 1.5 squared, which, what would that be? That would be 2.25, right? So it's getting a little bit larger, and it's hard for us to really understand what's going on because it's hard to do exponents of decimals as they get larger and larger in our heads. So intuition there is a little bit lost. Anyhow, there's a few ways that you could see this. Maybe the easiest way, we could plug into just some version of Excel. This way we can enter a bunch of inputs and do it with a formula. So I just want to enter. You could also do it on Google Sheets. It doesn't require much. So we could have our n column, let's say right here. I'll make this a bit bigger. We could have our n column, and then we could try to make a column with that 1 plus 1 over n raised to the nth power. So that's essentially the formula. And in Excel, what you want to do, you know, we could enter, let's say, 1, 10. We could double, maybe. Let's say 1, 2, 4, 8, 16. Oh, I should have said 16. And so on. So if we show it the pattern, usually you can extend it. Some number. Oh no. So thinks everything's additive. Why does it do that? It's not supposed to. Times 2 times 2 times 2 times 2. Yeah, 32. Why is it? I'm trying to do 2 to the y here, essentially. I'll just fill in a few by hand here. And I just want to show you, so how do you do the formula? Essentially, we do equals, and you don't have a variable, right? So we want to type in the same formula, but wherever we see an n, instead we're going to click the adjacent cell, A2. So we have 1 plus 1 divided by, and then I'll click A2, and then I'll close the parentheses, then I'll do the caret, and then again I'll click A2. So that's going to do the formula, and like I said, it gives 2, and then we're going to fill down. So what it's going to do is it's going to change that n every single time in our formula to the thing we have on the left-hand column, right? So it's going to plug in n equals 2, n equals 4, n equals 8, and so on. And I just want to show you that as n gets bigger, it does actually get closer and closer to this magical value, 2.718. So you might have to continue quite a while before it converges. Normally when you show it the pattern like this, maybe this is just an old version of Excel. Usually if you show it and then show it a number of terms, it will actually do the doubling. But see, it thinks it's like linear somehow. I don't like that. Anyway, you know, we could plug in, like, say, a really big number just to go one step further. Maybe let's try 100,000. See if it doesn't. Yeah. So there we go. We get 2.71827. So it's getting closer. The actual digit after that is 28. But you can see as you plug in larger and larger numbers, you get here. If you plug in something crazy big, you may get an error just because the computer doesn't have enough memory to do that formula, because you've got a lot of computations going on, and you know, as smart as our computers seem and as powerful. Anyway, so the moral of the story is, well, how do we do this? Well, on a calculator, there's a few different there's a few different ways it can look, but you don't just want to use 2.718 when you're trying to round. You're probably not going to get the correct accuracy because that would only be using a few decimal places. It's kind of like pi. If they ask you to do computations with pi, you want to use the best version of an unrounded source that you have. And so on this, it's going to be exp, and you also see just the e there. So you could have done it either way. So we can clear our previous thing out and do e. And notice that's 2.71828 and a bunch of other numbers that eventually start to look random to our eye. And then we hit the X to the Y button, and we want to do negative 0.79. What's that negative there? Yeah, so that's the correct value. So we want to type that in 3 places, so it looks like 0.454 or 0.454. And we get that value right there. So anyway, some backstory. If how many people in here have seen Euler's number before? Show of hands. Yeah. It comes up in compound interest formulas. So you may have seen it there if you've ever had those types of problems. Okay, so now we want to go ahead and just make a table of values. So this is not so difficult for number 3 here. we are doing f of x equals 5 to the x, and we want to make xy. I'm going to do a vertical table just because it fits better on this writing space. -2 up to 2. So to compute the y value, we're just plugging it into this function. So this would be 5 to the -2, 5 to the -1, 5 to the 0, 5 to the first, and 5 squared. So we all know that 5 squared is going to be 25. 5 to the first is 5. Anything raised to the 0 power is going to be 1. And then what does a negative exponent mean? It means you take the reciprocal and then do the exponent, right? So 5 to the -1 would be 1 over 5 to the first power. So that's just going to be 1/5. And then 1 over 5 to the -2 would be 1 over 5 squared, which is 1 over 25. So those are the values we want to enter here. Again, we're just plugging in numbers, but we're going to see that this will give us the shape of some exponential functions. So yeah. Okay, so what does that look like if we graph it? So again, these all represent ordered pairs. So you can see the all the y values are positive, so that means everything's above the x-axis. Yes? There's no half anywhere, is there? So remember the negative says that would be, so in general, if you have a to the -n, this is the same as 1 over a to the n. So that was actually an exponent rule from either module 1 or module 2 that we did. So for example, the 5 to the -2 that you're asking about is computed as 1 over 5 squared. So a negative exponent has nothing to do with the sign of the number. It's just telling you that instead you're kind of doing division rather than multiplication, because an exponent stands for repeated multiplication. So analogously, a negative exponent would in some sense stand for repeated division. So if you think of 5 squared as saying multiply by 5 twice, 5 times 5 is 25, 5 to the -2 would say, well, what if we divided by 5 twice? 1 divided by 5 times 5 would be 1 divided by 25. So dividing by 5 twice is the same as dividing by 25. So, yeah, okay, so if that clears that up, we can move on. And then these numbers are kind of like big and small, so we're going to use kind of a big scale here. So this is just going to be 1, 2, and then -1, -2 for our x values. That's no problem. But this goes all the way up to 25, so maybe we'll have, 5, 10, need room to make 5 marks, 20, and then up here we'll say this is 25. So we'll do a scale of 5 over here. So we know at the x value of 2, we have a y value of 25. So that's going to be all the way at the top here. And then at an x value of 1, we have a y value of 5. So that's right here. Then at 0, we would be down here at 1. And then a fifth would be very small. And then 1/25 would almost look like, with this scale, it's right on the x-axis. So we have this curve that's approaching the x-axis when you go to the left, and looks like it's almost moving very sharply toward infinity. In fact, if you think about the domain of this function, it will have domain all real numbers. So even though it looks like it's going up so fast, it does go all the way to the right forever and ever and ever as well. So as we see, this looks like the choice A. Okay, so this one is going to be similar. Let's go ahead and go through the table, and then I'll let you do this graph on. Well, we should do one of each, because essentially what happens is if you look at an exponential function, there's two possible pictures. So we'll note that this after doing number 4 here. But yeah, we really should do this, I suppose. So we have f of x equals 1 over 3 to the x power. So again, we want to do an x and a y, and we want to fill these things in. So we have -2, -1, 0, 1, and 2. Okay, so what do you think the value of 1/3 to the -2 is? So 1/3 to the -2, you would do the reciprocal, which means flip the fraction over, and then apply the exponent. So if you flip it over, you have 3, and then you're really doing 3 squared. So this 1/3 to the -2 is the same as 3 squared, which is 9. Which similarly would follow 1/3 to the -1 would just turn into 3. Anything to the 0 power is going to be 1. 1/3 to the first power is just going to be 1/3, and then 1/3 squared would just be 1 over 9. So those are our values. And then if you graph them, we're actually going to get something on the reverse, right? Our -2 is going to have a value of 9, and then they're getting smaller and smaller and smaller. The y values, they're always remaining positive. So, for instance, I can immediately rule out graphs B and C because they have negative y values on that graph. And I know that the y values here will never be negative. So, choice A is the safe pick. So let's just a recap for exponential functions, which is what we're looking at here. So exponential functions. Let's say exponential graphs. So anything, a general exponential function will look like y equals a times b to the x, where a and b are constants, and x and y are your variables. There's only 2 possibilities, and they only rely on knowing the value of b. There are some requirements for an exponential function on the 2 parameters a and b. One is that a must be positive, and the second is that b must be positive also and not equal to 1. Because if b were equal to 1, 1 to any power is always 1. So that wouldn't be interesting. It would just be a constant flat function y equals a. So the 2 possible graphs are related to the 2 we've just seen. So in general, the shape will always look like for growth, the first graph we did. This is the growth scenario. And then we have decay, which looks like the graph we just drew for 1 over 3 to the x. It looks something like this. So this is growth. This happens when b is greater than 0. And this is decay. This happens when b is between 0 and 1. Remember, b has to be positive and not equal to 1. So those are all the possible values of b. Where does that come up all the time? Well, you have lots of populations of things that will, if given an unlimited resource supply during that during a time frame, they will increase exponentially. So bacteria in some nutrient-rich fluid, often they will increase exponentially according to some sort of power. We see it in epidemiology, for instance, right? That talk about like if you have a virus that is where you're not imposing certain restrictions, and you have lots of interactions of people, susceptible individuals with infected individuals, then often that can produce an exponential curve. and often, you have different numbers associated with rates of diseases. So those are examples of exponential growth. Another one, just off the top of my head, compound interest, right? So compound interest, you set money in an account growing at a fixed percentage. Over time, that will grow exponentially. Decay happens with like lots of isotopes of unstable things. So like carbon dating, that's one of the reasons it works. The atoms of the isotope carbon-14, they decay into other things. We know how long that takes, so we can predict how old things are using that technique. Also, if you have a population that's experiencing a bunch of diminishing resources, say a food source or something like that, you could see an population of a certain species go toward extinction. That would be exponential decay. So these things come up all over the place in the real world. Okay, that's what all the pictures of the graphs look like. So this graph right here, number 5, we're trying to graph y equals 2 to the x plus 1. So I would do this in 2 steps. So are they using g of x? Let me write it because that's often helpful. We talked about transformations. So g of x would look like the first graph up there. It would just be an exponential growth graph. So if you do g of x equals, say, 2 to the x, you would get one of these growth graphs, right? And then if you talked about g of x plus 1, that would give you this 2 to the x plus 1. What is that? That is a composition transformation. So we're putting something inside the parentheses so that plus 1 is actually going to move the graph which way? Left or right 1? Remember? So g of x plus k units will actually move the graph left k units. So this shifts left 1 unit. So it would look pretty similar, but it would hit a slightly higher point. So let's see how we do that on here. We want to enlarge the graph. So the first thing you do when you're doing this is you go to the shaper tool. So what is the shape of the graph we're trying to do here? Well, it's this shape, that exponential shape. Oops, I did not want to. Okay, so what's a point we know on our graph? It's, well, on 2 to the x, it would be right there. All right, I'm clicking something wrong. I keep clicking the right click. Okay, so we have our graph 2 to the x. So the base is 2. That's what we want to select. The vertical translation bar, notice that's at 0 right now, that moving bar. The horizontal translation is what we want, and we want it 1 to the left. So we should want to slide that horizontal translation 1 left, I believe. And then just click OK. So what can we check? Well, we can check a couple of points, let's say. Just quickly to, I mean, this is correct, but for good measure, let's say we did, let's say we were doing x and 2 to the x plus 1, because that's the graph we're hoping to have. Let's just check 2 quick points. Let's check 0 and 1. So if you plug in 0, you will get 2 to the 0 plus 1, which is 1. You should get 2. And if you plug in 1, you should get 2 squared, which is 4. So on our graph right here, if you go to 0, x equals 0, you see the y value above it is 2. And if you go to 1, you see the y value above it is 4. So we do have the correct graph there. Keep clicking the wrong button. Okay, so let's go ahead and check that to make sure that whoa. So, yeah, so the g of x equals b to the x plus c. Oh, so I know what happens. They want you to graph the normal one first, I bet. Oh, no, we didn't graph its asymptote. So it's approaching the x-axis. So the x-axis is a horizontal asymptote. So we forgot to add that graph. Notice it says that in the instructions. Graph the function and its asymptote. Use a solid curve for the function and a dashed line for the asymptote. So we have to go back and edit this graph a bit. So that's all we need to do is add a line. So click the line shape, and then we want it to be dashed. So click the dashed version for coloring. And then we just can pick any 2 points on the x-axis there, and it will graph that. So that's all we left out. So now when we check the answer, we've got it. Okay, the equation of the asymptote, that's a horizontal line. So that's review from linear functions. A horizontal line just has the equation y equals whatever the y value it's on is. So x-axis is y equals 0. The domain of our function, as we talked about earlier, it's going all the way to the left and all the way to the right. So that is negative infinity to infinity. And the range of our function, it gets close to 0 but never quite gets there, and it goes up forever and ever and ever. So if you're thinking from bottom to top, on the graph of the solid line, it's going from 0 to infinity. Okay. So that's pretty much it with understanding the graphs of these things. Again, number 6 will be similar. We're not going to go through all the steps there. This one, notice the -6 is outside. So this is g of x in parentheses, -6 outside the parentheses. So that is a vertical translation. So this would be a translation of your 2 to the x graph down 6. So with that in mind, you should be able to answer the remaining questions. Okay, so we have these two compound interest formulas. As I said, they experience exponential functions as well. So for number 7 here, there's two formulas for interest. So if it's compounded a certain number of times per year, it's a finite compounding interest formula. And if it uses the word continuous, we use the continuous formula. So we have the finite formula. Again, you'll always be able to just look these up, but I do want to go through what all the letters mean, because that is what allows you to know what to plug in. And you have continuous. So A equals P times e to the RT. Reminds me of that shampoo. Okay, so A, that stands for the accumulated amount or future value. Future value or accumulated amount. P is the principal invested or the present value. R is the rate, the earnings rate or interest rate, and I'll make a note, this is as a decimal. So for instance, if it were 5%, you would not have R is equal to 5, you would have it equal to 0.05. N is the number of compound periods annually. And T is the time in years. So in the continuous expression, the only letter that is appearing there that doesn't, so notice N does not appear, but you do have E instead. And remember the definition, actually if you take 1 plus 1 over n raised to the n, and we made n infinity somehow, that would turn into E. So you can really kind of see one formula from finite turning into continuous. So again, E there is Euler's number. It doesn't represent anything that you plug in. That's the number that's, about 2.718. Okay, so for number 7 here, what we're looking at for part A, we have find the accumulated value of 15,000. So that's your initial investment. So P is equal to 15,000. I guess we don't need the dollar amount there. We have time is 5 years. Our interest rate, R, is 6.5%, so that's 0.065. And that's all we need, except for in each of the things. So in A here it says compounded semi-annually. So we didn't see N appearing in any place, but these code words will indicate the number of compound periods. So how many times per year does semi-annually mean twice per year or once every 2 years? Twice per year. Very good. So N would equal 2. If you said biannually, it would be every 2 years, and then I guess you would say N is 0.5 in that case. So then from there, it's really pretty easy. You have all your numbers. You just need to plug everything into your calculator. So we have A is equal to this 15,000 times 1 plus 0.065 over 2 raised to the 2 times the time in years, which is 5. So I don't know. I don't want people to think that's 2.5. So I'll do 2 times 5. Okay, so we have our calculator. Let's type that in and see what that will be. So I got 15,000. I probably should clear everything. Let's dump the memory there. So we have 15,000 times 1 plus the 0.065 divided by 2. Okay, and then I will say you have the exponent here, but when you're typing it in, you need to include an extra set of parentheses around the 2 times 5 in the exponent. If you don't, if you say just caret 2 times 5, your calculator will raise it to the second and then multiply the result by 5, rather than raising it to the 10th power. So I do need to include an extra set of parentheses here to the 2 times 5. So notice in the very top of that scientific calculator line, after the caret, I have parentheses around 2 times 5. So that's very important. If you don't include that, you might not get the right answer. So equals. So we get our answer. It said to the nearest cent, so that's the same as 2 decimal places. 20,000, 653.41. So the next one, B, it says compounded quarterly. Well, all the letters are the same now except for N. When you say quarterly, that means N is now equal to 4. So N's not equal to 2, N's equal to 4. So if I can go into my calculator here and just alter this, I don't know if I can just go up here and can I delete like a specific thing? Because that's all I need to do is change those 2 2's in the formula to a 4. So I don't know if this is kind of like a silly calculator, so it's not super interactive. So I don't think you can actually alter this top line where it's showing all of your actual computation. Yeah, I don't see a way to do that on this scientific calculator. Probably on other ones you can. So I don't know. We'll clear. We'll do the next line. I'm just going to type everything in again. And I'm just going to change the 2s to 4s. So we get our answer there, 20,706.30 when we round. Notice it rounds and then carries on that one, so that's a bit tricky for rounding as far as rounding goes. Monthly, same deal. I'm just typing the same thing, but now I'm changing those 4s to 12 because monthly is 12 times per year. That's something that's interesting, just two common ways that people are paid at a job. A lot of times people will kind of, what is the difference between being paid twice per month versus every 2 weeks? What is the difference over the course of the year? So if you're paid twice per month, that's 24 times per year, right? But if you're paid every 2 weeks, there's 56 weeks in a year, so you're paid 26 times. So if you're paid every 2 weeks, you get 2 extra paychecks over the course of the whole year. So that can affect some things sometimes. Or sometimes people make computations just assuming that, you know, even though it seems that they're roughly equal, you do have those extra pay periods to account for. Okay, so let's go back, do this last one with the 12. 15,000 times 1 plus 0.065 over 12 raised to the 12 times 5. Okay, so again we get 20,742.26. And I only went through all of these because I wanted to do the one continuous example. So the continuous example, we have much easier formula, 50,000 times E. So I can hit the E button, is that the easiest way? Times E raised to the, and then again you still want to put the exponent in parentheses there. So there it's R times T, so that's 0.065 times time frame 5 years. There's no values there, and that comes out to $20,760.46. So that's the most you can ever earn based on compounding alone, with all the other things held constant. So maybe we'll include D as well here. B and C not much different. For this one we just had to do 15,000 times E to the 0.065 times 5. And for both of these I guess I should have. So this was 20,760.46, and in A we had 20,653.41 dollars. Okay. On to the next. So in this one, what's going on is you have two different models that are trying to be used to predict the data of all the bars on the graph you see. So the one model is x plus 32, that's your linear model. And then the other one is the continuous exponential function. So for number 8 here, we have linear is f of x equals x plus 32, and then we have the exponential model, which is, this is just for this particular example that I have. Again, the numbers are going to vary from problem to problem. 32.9 e to the 0.0216x. Really, there's nothing hard here. You just have to understand the variables and whether we're plugging it into linear or exponential, or if they're asking potentially about the actual data from the graph. So for part A here, it says according to the linear model. So plug it into the linear model. What percentage applied to more than 3 colleges in 2013? Okay, so what is X? It tells me that X is years after 1980. Okay, so 2013 is how many years after 1980? Well, that's 33. So that means plug in 33 for X. A mistake I might see there from a lot of people is they might just plug in 2013 and then get a humongous number. You should note that whatever value you should get should probably get close to the actual value on the graph 68, at least in the ballpark. So f of 33, we get 33 plus 32, which is 65. Right, so this is part A. So 65%. Then in B, they say, use the exponential model. Okay, so for B, we want to do the same thing, but we want to plug it into this G formula. So we have G of 33, which is 32.9 times e to this 0.0216 times 33. Right, we're multiplying everybody in the exponent. And remember, you want parentheses around those when you plug it into the calculator. So, right, the linear is pretty easy. You can just kind of do that in your head. But when we are performing this computation, we need the calculator. So we have 32.9 times e times e raised to the 0.0216 times 33. So we get our answer here. It says round to the nearest percent, so we're just going to say 67. Which is a better model? Well, what were our two values again? We know 67. The real value is 68, so 67 is going to be closer. We had 65 for linear. So for that particular year, the exponential model was closer to the real value of 68 than the linear. Okay, so now we're going to start talking about logarithms. So the way to think about logarithms is the inverse operation of exponentials. So this is, I don't know, some students find this to be maybe the more challenging part of the course, but we can kind of think of this, so logarithms. So what the heck is a logarithm? So the main definition here is it's the inverse of this exponential idea. So if we have, let's say, y is equal to the log base b of x. The way to think about this equation is to rewrite it and think of it as an exponent in another equation. So this is equivalent to b to the y is equal to x. Okay? And one way to evaluate, you can't always evaluate these in your head, but for a lot of numbers you can, and you can evaluate them essentially if you can answer this question. So to evaluate, just if you have the log base b of x, and b and x are both regular numbers that you can see, what you want to do is answer the question, what power of b makes x. So, for instance, if I had, so for example, if you had, let's say, the log with a base of 7 of, I don't know, yeah, let's say 343. To evaluate this, you would have to answer what question? Well, x is the number inside the parentheses, and b is the number on the bottom there. It's actually smaller. You know how exponents are superscripted? Well, in this case, 7 is subscripted. That's how it's supposed to be written. So you're really just answering what power of 7 makes 343. Well, if you do 7 to the third power, you get 343. So your answer there would be 3, and that's because 7 to the third power is 343. And again, if it said something like log of 7 and then in parentheses 10, I couldn't do that because I don't know what power of 7 makes 10. I know it's more than 1 and less than 2, but that's all I would know. Because 7 to the first power is 7, 7 squared is 49. 10 somewhere in between the two. Okay, so for this first example here for number 9, again, I'm just going to write down that definition we had. Y equals the log base b of x. The way to rewrite that to the exponential equation is you do b to the y equals x. So a lot of times when you have this, you're really just matching up the things. So we have 2 equals log base 3 of 9. So if we want to rewrite that, well, 2 is equal to y, and b is equal to 3. So we have 3 squared, and x is the number inside the parentheses. 3 squared equals 9. That's what they want us to write down for this problem. So 3 to the second power is equal to 9. Write this in its equivalent exponential form. Again, same problem. Number 10, we have y equals the log base 4 of 64. So, how would you rewrite that? Well, you take the base, write it there. So 4 to the y is equal to the number in the parentheses. So 4 raised to the y equals 64. You're not really solving anything, you're just rewriting it according to its definition. So 4 to the y equals 64. All they want you to do. This one is going the other way. So we have number 11 here. So again, this time they're starting on this side. So remember the rule is we want to take b to the y, that equals x, and on this side it's y equals the log base b of x. So they're starting on this side. 3 to the second is equal to 9. Well, that makes 2 the value of y. The b value is 3. And what's inside the parentheses is the other side, 9. So that's all you're doing. Switching from one side to the other, just apply that definition. So if you make a mistake, just write down the definition in front of you, and if you have to, write b equals this number, y equals this number, x equals this number, and then just fill them in on the other side. So 2 equals the log, and then subscript is down here between this root and the ordered pair symbol. So this is the subscript. So log base 3. And for log, you can just type log. And you don't really need the parentheses I put around the 9. I just like to have them there, but you can do it either way. So you can leave it like that. Again, this one's going to be similar, so we'll pass over number 12 here. But you're just switching exactly like number 11. Okay, find the exact value of the logarithm without using a calculator. So this is what we get into. So these are not so bad. This is just the basic properties, or not the properties, evaluation using that question method I said before. So if they say evaluate log base 7 of 49 like this, you're just trying to answer what power of 7 equals 49. That should be easy, right? 7 squared. So the power there is 2. What power of 6 makes 1? What do you raise 6 to that gives 1? Well, raising something to 0 always gives 1. So 6 to the 0 power equals 1. So the thing you raised it to is 0. That's your answer. So now we want to graph 3 to the x and log base 3 of x. Well, we already have a sense of what 3 to the x looks like. 3 to the x looks like exponential growth, right? So exponential growth is going to the x-axis on the right and exploding toward infinity on the... So going to the x-axis on the left and exploding toward infinity on the right. So that graph appears in, some version of that graph appears in A, B, and D, but we don't see it in C, so we can roll that out. But really what we want to do is figure out the graph of the log base 3 of x. So if we want to graph log base 3 of x, we need to plug in some values and then be able to evaluate them. The thing here is, if we want to be able to evaluate them, we can't just plug in any old thing, right? Because if I plug in an x, I have to be able to answer that question to figure out the y value, right? What power of 3 makes x? Okay, so one thing that's interesting, if you're trying to think about what kinds of things can you plug in, can you plug in a negative number? So if I had something like log base 3 of, say, negative 3, what power of 3 makes negative 3? Well, what would the answer be there? There's in fact no such number. You can't do it, right? If you take 3 and you raise it to any power, it's always going to be a positive number, right? 3 to the x is a graph that's completely above the x-axis. It only has positive numbers. Well, what about 0? It gets very close to 0, but never actually gets there. So the log of any negative or the log of 0, so the log base 3 of 0, both of these are undefined. So when we're making our chart here, we can only plug in positive x values. That's one place to start our understanding. Another place is to think about answering that question. What power of 3 makes? Well, x is the thing we're asking about. What power of 3 is x? Well, that means if we want to do it in our head, we probably want to plug in powers of 3, right? Because that would make the question very easy. So what are some powers of 3 that are easy? Well, either 3 raised to some power or 1 divided by 3 raised to some power. So if I did, say, 1 over 9, 1 over 3, 1, 3, 9, and so on, those are all numbers that I can do. And then your answer would just be the exponent of 3 that makes that happen. So 3 to the negative 2 is equal to 1 over 9. So this would be negative 2, negative 1. 3 to the 0 is 1. 3 to the first power is 3, and 3 squared is 9. So if you can see, this logarithm is really acting like the opposite of 3 to the x. It's really an inverse function because we are switching our inputs and our outputs around. So if you did 3 to the x, and you started on this side, you would really go here, right? 3 to the negative 2 is equal to 1 over 9. 3 to the negative 1 is 1/3. 3 to the first power is 3. So you're really flip-flopping, switching around your x and y values from 3 to the x when you're doing the log base 3 of x. That's why it's the inverse function. One way to think about the graph of a function and its inverse is it's reflected about y equals x. So that's actually exactly what's going on here. If you just, so you can graph that, or you can do the sketch. So if you have your exponential guy, which in this case is y equals 3 to the x, we have y equals x, which is the 45-degree line through the origin. The machine froze on me, unfortunately. Sometimes I just open too many tabs. Let me see if I can get it out of this. If not, I'm going to have to reboot. That's no good. Sorry. We only have a few more to do. We're probably only going to go 15 more minutes and then go, but yeah, I think I have to reboot. Sorry. Okay, so the computer froze and we had to reboot. So that's why on the homework it's now 4 to the x and log base 4 of x, but talking about the graphs is going to be similar. So if you look at this dotted line, this would be y equals x. So then the reflection would be down here, and that would be the graph of the log. So if you think about flipping this over this dotted line, you would get exactly something that looks like this. So this is the graph of a log. In general, you're going to have two possible graphs of a log, right? One that has a shape according to exponential growth, and one that's a log according to something for exponential decay. So here, the base was 3, so this is like an exponential growth one. Okay, which one looks like that? D. Okay, so here we have an exponential decay. I'm just going to kind of do this one quickly because although we can plug in all the points and do the same flipping around and graphing them, that's all we really need to do is draw a generic exponential decay, draw our y equals x dotted line, and then do the reflection. So graph y equals 1/6 to the x, and because they're not looking for anything specific, right? We just need the two shapes. Y equals log of 1/6. So if we graph our general exponential decay, that's going up on the left and getting close to the x-axis on the right, we'll call this y equals 1/6 to the x. Then we want to draw our dotted line. So this is y equals x. Now we have to reflect to figure out what the log graph is going to look like. So if it's getting close to this side of the axis, now the log graph should get close up here. They should pass through the same point, and then it should go this way. So this is going to be your y equals log of 1/6. to the x. So these two actually do cross. Anytime you would touch the y equals x line, both of those need to be at that point, right? So they need to connect there. On the previous one, neither y equals 3 to the x nor y equals log base 3 of x, or yeah, log base 3 of x, neither of them intersected that dotted line that was down the middle. So as we can see, that looks to me like, I believe A, let's make that a bit larger so we can see. Yeah, so notice they're crossing right there on that y equals x horizontal line. So that looks like the correct choice. Okay, so yeah, so maybe let's make that note. In general, the shape of y equals log base b of x, right? If we're just thinking about the log graph on its own, it looks like this, where the y-axis is a vertical asymptote going down, or this one, where you still have the y-axis as an asymptote, but instead it's on the upward side. So when does that happen? It happens in this case when you had exponential growth, which is b greater than 1, and exponential decay for this one when b is between 0 and 1. So notice the base of 3 was greater than 1, but 1/6 was between 0 and 1. So what are we doing here on this particular problem? The graph of the logarithmic function is given. Select the function for each graph from the following options. Oh, up there. So it's a drag and drop kind of problem. Maybe I can zoom out. Yeah, so there we go. So log base 3 of x, I'm just looking at this f of x here on the end. That one just looks like a regular old log graph. So it should have the y-axis as an asymptote. And we also know, for instance, that, so in my mind it would have to be this graph or this graph. I know it's this graph. Why do I know it's this graph? Well, if you ask yourself, what's going on where it crosses the x-axis? This one's crossing the x-axis at 1. Up here, this is crossing the x-axis somewhere else. It looks like at 3 maybe. So if you do the log base 3, or let's say if you do f of 0, I'm getting confused about how to say it. So this is saying when you plug in x equals 1. Yeah, so when you plug in x equals 1, you should get a value of 0. And that makes sense because 3 to what power equals 1? Well, 3 to the 0 power equals 1. So that's why I know that that one has to be log of that. Now all of these other ones are just some form of transformations of this graph. What is the easiest one to recognize? Well, in my mind, g of x now is the easiest one to recognize. If you have that graph and then you do x minus 1, what kind of transformation is that? Well, that's a horizontal transformation. And which way is it shifting it? Left 1 unit or right 1 unit? This will be right 1 unit. So now your vertical asymptote is not the y-axis, it's one step to the right of the y-axis. Well, which graph looks like it's one step to the right of the y-axis? Down here, number 51. Okay. What happened here? This one looks like some kind of vertical shift, maybe? Maybe a shift down? Because now, like I said, instead of crossing the x-axis at 1, like 52, number 49 is crossing at 3. So somehow you're shifting it down. That's my guess. What's the only thing that would shift something down? Well, h of x. the -1 is not inside parentheses, it's outside parentheses. So this should be a shift downward. All right. So now what do I see? I see a bunch of things that involve reflections. According to the formula, what is the simplest reflection? Well, it's that capital G of x, and that capital G of x is a negative inside the parentheses. That is a reflection across the y-axis. So if you take your original graph down here and you reflected across the y-axis, if you reflected number 52 across the y-axis, you would get the graph for number 48. All right. Now the other simple one is the negative in front. So it's not inside the parentheses like capital G of x, it's in front. That's going to take your original graph and just flip it about the x-axis. It's going to make all of your y values the opposite. So if you look at 52 and you imagine flipping that around the y-axis, what would that look like? Well, in my mind, it would look like 50. Because if you flipped the point on the x-axis, it would stay in the exact same place, right? So that point that hits the x-axis at 1 should still be hitting the x-axis at 1. So that's 50. Because 47 is hitting the x-axis, I don't know, somewhere else. So I know capital F of x needs to be graph 50, and 47 is the remaining one by process of elimination. Again, you could go type all these into graphing calculators and do it that way, but you can also use your understanding of transformations to just deduce which should be which. So that relies really on other things. Okay, again, probably just a couple more of these and then we'll be done. So there's two special logarithms that we talk about. So the common logarithm, and this is just special notation. That's all this is. So if you write y equals log of x, this means y equals the log base 10 of x. So since this is so frequently used, we just don't write the 10. It's kind of like for the cube root, you've got that little 1/3 up there, but when you're doing a square root, you don't write 1/2. It's just so common, it's the most common one, so we don't write anything. So for instance, on number 18 here, when I have the log of 1/100, I'm just asking the base, although it's not appearing, I know that it's 10. So what power of 10 makes 1/100? Well, I know 10 squared is 100, so if it's in the bottom, it's the reciprocal, right? So this is -2. So the answer here is -2. 10 to the -2nd power equals 1/100. So that's one of your exponent rules. And then the other special logarithm is known as the natural logarithm. So the natural logarithm is ln. So y equals ln of x. And basically this means y equals the log base e of x. So this is also very important. This is one of the very important functions in calculus because of properties to do with the derivative. So since it's so common, we don't want to write that base all the time. So they have a special notation instead of writing log with that base of e. So again, you're just answering e to what power equals x. So that's it. So for number 19 here, if you have ln of 1, we're asking what power of e makes 1. So e to what power makes 1? Well, e to the 0 power. Anything to the 0 power will make 1. So the answer there is 0. Okay. So we'll stop right here. This is a good stopping place. Some other properties. We'll move on with the logarithms. We haven't gotten to the properties of logarithms or solving equations with logarithms, which is going to be kind of an involved topic. It requires a little bit of tricky algebra, but we'll go through those. So anyway, we will finish part 1 of the video right here. Thanks.